Okay, if we go ahead and look at this problem, this one was a little bit vague because it didn't give you information about what the masses were. It doesn't matter what the masses are because the ratio will be the same. So it's your choice. I randomly chose 10 grams of each. So 10 grams of pentane, 1 mole is 72 grams. I got 0.139 moles. 10 grams of heptane, molar mass of 100, 0.208 gave me 0.0997 moles. So I calculated the mole fraction of the pentane as 0.582, the mole fraction of the heptane as 0.418. Then the pressure of the solution is equal to the mole fraction of the pentane times the pressure of pure pentane plus the mole fraction of heptane times the pressure of pure heptane. And when I add these together, I get 259 torr. So the biggest problem I have seen with my students when they do this type of problem is that they get the pairs wrong. They'll go through all the math calculating their mole fractions, and then when they go back and read, they'll take the mole fraction of pentane and hook it with the pressure of heptane just because they're not paying attention or they're in kind of a hurry on a quiz or a test. So that would be the most likely thing that you would do wrong. Now, when we're looking at this, we can think of building sort of a visual representation in a graph for Raoult's law. And we talked about Raoult's law being for ideal solutions where the enthalpy of solution is equal to 0. There's no energy change because we have the same attractive forces between the two different types of molecules. So when we build this graph, it looks like this, and it's kind of a strange looking sort of graph. Over here, we have the mole fraction of A, and over here, we have the mole fraction of B. So here, the mole fraction of B is equal to 1, and over on this side, the mole fraction of B is equal to 0. Here, the mole fraction of A is equal to 1, and over here, the mole fraction of A is 0. Does that make sense to you? That on this line, I have pure A, and then the amount of A I have is decreasing as I go across. And over here, I have pure B, so I have 0 B here, and I'm increasing B and decreasing A across. That's what these labels mean. So when I look at this, if I'm looking at the pressure on the y-axis, when I have A, pure A has some vapor pressure. So this is the pressure of pure A. Over here, the pressure of pure B has some pressure. So when I look at this, what's the pressure of B over at this line? 0, because there is no B. So if I draw a straight line, well, I missed my dot, but if I draw a straight line to my dot, this tells you the pressure of B at any mole fraction of B. Does that make sense? Now, what's the pressure of A over on this line on the right side? 0, right? So hopefully I can draw a straight line now between, well, I couldn't, between those 2 points. Okay? So this is the pressure of A. So at any point in time, I can look at the pressure of B and I could look at the pressure of A, and if I add them together, then I get the total pressure. And so all I need to do is to connect the two dots, and this line, the dotted line for the total pressure, is equal to the pressure of A plus the pressure of B. So instead of doing all that math, you can look at this, labeled the mole fractions, and you can just read the numbers off a chart if there were numbers on this. So chart reading is one of the skills you need in Chem 112. So I expect that if there were a chart in front of you, you could read it and you would know how to interpret. If it said if the mole fraction of A is whatever, go here, go to the total pressure. There you go. That's how you read a chart. Now, that is for an ideal solution. In the real world, sometimes we get deviations. So now I'm going to try and reproduce that twice. So if I try and reproduce that, this is the same thing I drew previously, even if it doesn't look exactly like it, right? So over here I have the mole fraction of A is 1. Over here the mole fraction of B is 1. Now sometimes instead of that straight line, when I actually connect the dots, here's what happens. I don't get a straight line here. I get a line like this that goes up. So when that line curves up, the pressure is higher. And that's because the intermolecular attractions that the two materials have for each other is less than the intermolecular attractions for the pure material. So if the two different components aren't holding on to each other as tightly, it can evaporate more easily and you get a higher vapor pressure. You can have the other thing happen. Instead of a straight line going here, we get our dotted line sinking down. And that's because the intermolecular attractions between the two components is stronger. So they're holding on to each other more tightly, which means less can evaporate and you get lower vapor pressure. Okay? So that's kind of what happens with the whole Raoult's law thing. Now we're going to take this and we are going to go and look at a graph or a chart that we looked at in Chem 111. In Chem 111, we introduced the phase diagram. And on the next page in your packet, you will see a phase diagram for water. Now, yours is in black and white, and I'm going to show you one in color. But do you see there's a dark line here and a very pale line here? Okay. Your dark line is the lower line, which is the darker one. I'm calling this red because it's red on my color copy. And then the line up here, the paler one, this is blue. So when I talk about red and blue, the dark line on your copy is red and the paler line on your copy is blue. So what happens here is that the blue curve is for water, pure solvent, and the red curve is for a solution that is made of this material. So when you think about this, we look at this new diagram and you'll notice that I have this dark line separating the solid, the gas, or the liquid and the gas, and this line did not change. The line between solid ice and water vapor, the sublimation line, did not change. But over here, I have a new, different line. This line has shifted. And what's going on there is this. When you have a non-volatile solute, like salt in water that we had in lab, and you boil off the water, what happens to the salt? It stayed behind. So there was no salt in the water vapor, correct? So I have salt in the solution, but here I had pure water vapor. Does that make sense? The salt didn't evaporate. Now think about freezing. Think about the Titanic. You know the Titanic, right? If you'd been on there, you're dumped in the water, now you're swimming because you didn't make it in one of the boats, but you see the iceberg that raised all the ruckus over there. So you think, well, that's floating, I'll go climb on the iceberg. So you go climb on the iceberg, now you're a little thirsty, so you lick the iceberg. And hopefully your tongue doesn't stick. What do you taste when you lick the iceberg? Water. Did you know that icebergs are fresh water? They are. Yeah. Because when the solution freezes, the salt doesn't go in the crystals. Only the water goes in the crystals. So icebergs are actually fresh water. So the solid is water only. The gas is water only. And this is water and salt if we're talking about a saltwater solution. So what's happening here is that because we don't have any solvent, or we don't have any solute going into the vapor, when we have the solution and we're going into the vapor, we're going to have a lower vapor pressure for the solution, right? We just figured that out with Raoult's law. The solution has a lower vapor pressure. If the solution has a lower vapor pressure, what does that affect? How does that affect the boiling point? We talked about this in Chem 111. It raises it up. If the vapor pressure is lower, you have to crank up the temperature to get the vapor pressure high enough to be the prevailing atmospheric pressure, because that's boiling point. So here's what happens. This line that is the water blue line shifts. And if you look at this, you get a higher temperature for the solution to boil. That phenomenon is known as boiling point elevation. Over here, the opposite thing is going on. You have the solution, but only the water is going into the solid. So it takes longer for that to go into the solid because they have to get around those solute molecules. So you get this line shifting the opposite direction. These are lower temperatures. That phenomenon is known as freezing point depression. So when we have a solution, the sublimation line is not affected. Pure solid water, pure water vapor. But the solution to water vapor and solution to freezing lines are affected. So now we have these two phenomena, and they are also colligative properties.